dear students, here let us talk of solution of transmission line equations in phasor domain. Already we know that actually dou square Exs divided by dou z square is equal to gamma square Exs. This was the equation in the uniform plane wave. So if you see the solution of this one, Exs is equal to ER0 e power gamma z plus EI0 e power minus gamma z. So it was the electric field equation of the incident wave or otherwise wave traveling in plus z direction. It was the electric field equation of the reflected wave or otherwise wave traveling in the minus z direction. So similar to this here, dou square Vs divided by dou z square is equal to gamma square Vs. So in place of Exs, Vs is there. So solution is similar. Solution of this is numerator variable, that is Vs is equal to Vr0 e power gamma z plus Vi0 e power minus gamma z. Now here the notation, that means symbols are changed. Vr0 means initial value of the reflected voltage, and Vi0 is initial voltage of incident wave. So this wave travels in plus z direction, so that is why it is given symbol as V plus. In some books bottom side they write, here we have written in affix. Affix मतलब ऊपर है, suffix मतलब नीचे लिखता है कुछ books में. So V plus e power minus gamma z. This is the wave traveling in plus z direction. So initial value of this is written as V plus. Here plus stands wave traveling in plus z direction. Similarly, Vr0 is written as V minus e power gamma z. So here what is this? This one is what? This is a voltage equation of wave traveling in minus z direction, or otherwise it is a voltage equation of reflected wave. Similarly, this one, this is a voltage equation of wave traveling in plus z direction, or otherwise incident wave. Okay, I am going to show you clearly. Physically meaning I will explain, because we will not waste much time in the solution of these equations. That is the absolute wastage of time. So let us say this is equation number 1. The solution of this is this one. So you can put this in the box. Okay. So this is equation number 2. Similarly, current equation is dou square Is by dou z square is equal to gamma square Is. So ultimately the solution of this is I of s is equal to, similar to this, I minus e power gamma z plus I plus e power minus gamma z. So this is the current equation of wave traveling in minus z direction, or otherwise reflected wave. Okay, and this one is current equation of wave traveling in plus z direction or otherwise it is called incident wave. Okay, so this is equation number 3. This one is equation 4. This is in the box. Okay, here I will write what is V plus, what is I plus. I will write everything. So now I will explain you the meaning of these solutions. You can see here. So this is the transmission line like this. This is the conductor and like this. Here this is ZG, this is VG plus minus. This is the load and this is Z is equal to 0. Okay, at Z is equal to 0, the initial value of the incident voltage is V plus. Then at Z distance, because in wave traveling direction, this value decreases. Decrease means actually V plus e power minus gamma z. Decrease means an exponential minus should be there. Similarly, a reflected wave voltage at z is equal to 0, initial value is V minus. Now when it is coming here and in this direction, this value reduced and remaining this much, here more value should be there. So V minus of e power plus gamma z. So actually briefly I will tell you students, at z is equal to 0, initial value of the incident voltage is V plus. Now when this voltage comes here at z distance on the transmission line, this becomes V plus e power minus gamma z. That is the meaning of this one. At z is equal to 0, the incident voltage is V plus, and when it travels z meters distance, it has become V plus e power minus gamma z. So this one. Similarly, at the z is equal to 0 distance, reflected voltage initial value is V minus, and at z distance, that value is V minus e power plus gamma z. Here more value is there. In the wave, reflected wave travels in reverse direction. In this direction, voltage should reduce. It has reduced and remaining V minus value. That is the meaning of this. So total voltage on the transmission line at z distance is equal to, here this is incident one, V plus e power minus gamma z, plus this is reflected V minus e power plus gamma z. Here you can write this one at the beginning or you can write this one later, doesn't matter students. So here at z distance, incident voltage, that's what I have written here. Incident wave voltage is V plus e power minus gamma z. At z distance, reflected voltage is V minus e power gamma z here. Okay. Now, similarly, for incident wave at z is equal to 0, current is I plus, and for reflected wave, here current is I minus. I minus. Now in same way you will write the equations here. Now at this location, it has become I plus e power minus gamma z, and here at this location it is I minus e power plus gamma z actually. So this is I minus e power plus gamma z, and this one is incident current is I plus e power minus gamma z. So total current at z distance is again this equation only. Okay. So here I will write V plus means initial voltage, that means at z is equal to 0. Initial voltage of incident wave. What is the meaning of I plus initial current, that means at Z0 of incident wave, V minus initial voltage, that means at Z is equal to 0 of, I will write for this, so initial voltage, that means at Z is equal to 0 of reflected wave. I plus I minus is initial current of reflected wave. Now you have seen the solution. It is very simple. The solution is in the form of exponentials only. So you have seen the equations, and I have shown in the diagram also. Now, for example, here total length of the transmission line is L. If the total length of the transmission line is L, maybe small l or capital L you take, doesn't matter. So total length is L. Then here load current is actually IL, and at the load total voltage is VL. Okay, plus minus. So load voltage by load current is defined as ZL actually. Let it be like that. Now, what is the relation between V plus I plus and V minus I minus? That relation is obtained by taking the phasor equation, which gives relation between voltage and current. So already we know that dou Vs divided by dou Z is equal to minus Z into Is. This is equation number 5. Now Vs solution, that means S means steady state, Vs solution, this one, that is equation 2, and Is solution, that is equation number 4. If you substitute here and compare the e power gamma z terms and compare e power minus gamma z terms, then you get relation between V plus I plus V minus I minus. So substitute equation 2 and 4, put equation 2 and 4 in 5. So dou by dou z of Vs is V minus e power gamma z plus V plus e power minus gamma z, that is equal to minus z into Is is actually I minus e power gamma z plus I plus e power minus gamma z. So this, if you differentiate this one, V minus d by dz of this one is e power gamma z into gamma plus V plus e power minus gamma z into minus gamma. So minus z I minus e power gamma z minus z I plus e power minus gamma z. So you can remember in this way. Here plus means wave traveling in positive. This is initial value of wave traveling in positive z direction. Then here minus gamma should be there in the exponential. Similarly, V minus means initial voltage of the wave traveling in minus z direction. Minus stands here, opposite sign should be there, plus should be there. So here, dear students, you compare now compare e power minus gamma z terms both sides. Then what you get here, e power minus gamma z na V plus into minus gamma is equal to here minus z I plus. So from this V plus divided by I plus here na is equal to minus minus gone. So you get z by gamma. So z divided by root zy, z cancel, and root z by y remains. So this one is nothing but root of r plus j omega l. divided by G plus J omega C. Now it is defined as Z naught. The definition is given here because voltage by current is impedance, so that is why it is impedance, and it is a function of four characters of the transmission line and frequency. That is why it is defined as characteristic impedance. So now here you got V plus by I plus is Z naught, characteristic impedance. Similarly, compare e power gamma z terms, both sides, this one V minus gamma is equal to minus of z I minus. So V minus divided by I minus is equal to minus z divided by gamma, that is minus z divided by root zy. So root of z divided by y, and this is defined as minus z naught. So from this, what is the conclusion? V plus by I plus is equal to characteristic impedance, and V minus divided by I minus equal to minus of characteristic impedance. The meaning of this is for reflected wave, power should go in reverse direction. For that, either reflected voltage or otherwise reflected current should have opposite sign. You can easily see here, and the incident voltage plus minus, and the reflected voltage also plus minus, but incident current is like this, and reflected current is opposite. So indicating that power flow for the reflected signal should be in reverse direction, same as uniform plane wave chapter. Okay, now from this, what is the ZL in terms of voltage and current? Load impedance is equal to load voltage divided by load current, like network theory. So VL divided by IL, and in equation number 2, if you substitute Z0, then total voltage at the sending end is incident voltage plus reflected voltage, that is V plus plus V minus. That's what you get. Similarly, in this, put Z is equal to L. Here L comes, then you get voltage at load you get. Similarly, in this equation, you put Z is equal to L, total length of the transmission line, then you get total current at the load. So VL by IL, that is the equation. I am writing that here. Okay. So here ZL is equal to VL divided by IL, that is nothing but here in this, if you substitute Z is equal to L, you get V minus e power gamma L, and V plus e power minus gamma L divided by, you substitute Z is equal to L in this, so I minus e power gamma L plus I plus e power minus gamma L. Okay. Now from this, I plus is equal to V plus by Z naught, I minus is equal to V minus divided by Z naught, minus sign should be there. Okay. So here I plus is equal to V plus by Z naught here, no? So that is equal to V minus e power gamma L plus V plus e power minus gamma L divided by I minus is minus V minus by Z naught e power gamma L plus this one is V plus by Z naught e power minus gamma L. Actually, I wrote here I minus and I plus in terms of V voltages so that we can pull out and cancel them, and denominator common Z naught, it goes to numerator. So ZL is equal to Z naught into here V plus e power minus gamma L I will take common. So in the numerator v plus e power minus gamma L. Then what will happen? I will get 1 plus v minus e power gamma L divided by v plus e power minus gamma L, and divide by, here is the Z naught, that is ZL. So here similarly v plus e power minus gamma L is the common, v plus e power minus gamma L is the common, then ultimately we get 1 minus of v minus e power gamma L divided by v plus e power minus gamma L. Okay. Let us say this is equation number, till now how many equations we got? Equation 5. So I did not give, this is equation number 6. Okay. Now what is this actually? I am going to write this in separate note. Here derivation is going on. In this derivation we have seen solution of voltage equation, solution of current equation, then what is the relation between V plus and I plus, what is the relation between V minus and I minus, and we are finding ZL in terms of gamma L. Now what is this actually? V minus e power gamma L, V minus e power gamma L, that is reflected voltage at load, then V plus e power minus gamma L, that is incident voltage at load, that is defined as reflection coefficient at load actually. Okay. So here you can see, dear students, for example this one at load it has become V plus Z is equal to L, V power minus gamma L, and at the load this reflected voltage is V minus e power gamma L. Then total voltage at load, already you have seen total voltage at load is equal to VL is equal to V plus e power minus gamma L plus V minus e power gamma L. That's what I wrote there. So anyway, now reflected voltage at load, that is V minus e power gamma L, divided by incident voltage at load, that is V plus e power minus gamma L. So it is defined as the reflection coefficient at load, that is the definition. So I will be writing this separately. So this is reflected voltage at load divided by incident voltage at load. So this is the reflection coefficient at load. So if you put this here, this one cancel. So from that ZL is equal to Z naught here 1 plus gamma L divided by 1 minus gamma L. Okay. Let us say this equation number 7. And if you cross multiply them, ZL, ZL minus ZL gamma L is equal to Z naught plus Z naught gamma L. Okay. Now you get this this one this side, and you send this one this side. So gamma L into ZL plus Z naught is equal to ZL minus Z naught. That implies gamma L is equal to ZL minus Z naught divided by ZL plus Z naught you got. So this is equation number 8. Here so many things we have derived, dear students. What is voltage equation on the transmission line, what is current equation, then you have seen the diagram also, we have written the names, so you must know them. Then after that we have got the relation between V plus I plus and V minus I minus. So for reflected wave, power should go in reverse direction, that is why V minus I minus, one of them will have minus sign, so that the ratio is minus Z naught. And here we have derived that gamma L is equal to ZL minus Z naught by ZL plus Z naught, and also ZL is equal to Z0 into 1 plus gamma L, 1 minus gamma L. This is the equation used to draw the Smith chart. I will tell you later on this one. Now we are going to write the note for reflection coefficient. Okay, so reflection coefficient. See here, note, first one, gamma L is equal to reflected voltage at load divided by incident voltage at load, that is equal to V minus e power gamma L, V plus e power minus gamma L. So this is the definition. Now after doing derivation, we got this gamma L is equal to, so it is also written like this, students. Simply V reflected divided by V incident, it is written. So anyway, this is equation number 1. So gamma L is equal to ZL minus Z0 divided by ZL plus Z0. In general, this one is complex. So every complex number has a real part and imaginary part. So that has magnitude and angle, modulus of gamma L, e power j theta gamma L. Okay. Now this one is complex actually. Complex number has magnitude and angle. This also you have to remember. So here gamma L is reflection coefficient at load. Reflection coefficient at load. Then mod gamma L, the magnitude of reflection coefficient. Theta gamma L is angle of reflection coefficient. Okay. Next, gamma Z is nothing but reflected voltage at Z distance divided by incident voltage at Z distance. So that is equal to reflected voltage at Z distance. Already you have seen V minus e power gamma Z. Incident voltage is V plus e power minus gamma Z. So this is the equation. Let us say this is equation number this is 2 and this one is 3. We will be using that also. This is 3. Okay. Now here I will draw one diagram. See this diagram here. I will write the statement and then I will. Reflection coefficient at d distance from load end is obtained by putting Z is equal to L minus D in equation 3. Now what is that? I will draw the diagram here. So this is the transmission line and this is ZL. Okay, this is ZG, this is VG. Now this is Z0, this is at Z distance. Total length is L. Now this one is D is equal to 0. Okay, now you come here for actually I will explain like this. For example, let us say total length is 10 meter. One student asked me to calculate the voltage at Z is equal to 2 meter from the source end. Then what I did not calculate the voltage at 2 meters from source end. I have calculated voltage at 8 meters from the load end. 8 meters from the load end. That means if I calculate voltage at 8 meters from load end, that gives voltage at 2 meters from the source end. That means from this you understood that we can do calculations from load end also. Okay, that is famous because generally matching is done at loads. So calculations are done from load side only. That is more simpler. So here Z is a parameter used to measure the distance from sending end, and D is the parameter used to measure the distances from load end. D is equal to 0 means at the load. D is equal to L means then at the input end. So I will write that later on. So in this way, now for example, now here D is equal to 8 meter. Now if Z plus D is equal to L, that means this is 2, this is 8, this is 10. If Z plus D is equal to L, then Z comma D locations are same. Now from this what is Z value? L minus D here. Z is equal to L minus D. So if you substitute here Z is equal to L minus D in this equation, then we get the reflection coefficient at D distance from the load end. Why are you substituting this equation? To make sure that both the locations are same. That is why you have to substitute. That is written here. Okay, now I will remove this example. No? Okay, now here you substitute now reflection coefficient at D distance from the load end is obtained by putting Z is equal to L minus D in equation 3. So V minus e power gamma Z is equal to L minus D divided by V plus e power minus gamma L minus D. Actually derivation is going on, student. Derivation is going on. Actually from that I told you to remember this one. After this some derivation is going on. Here you need not to remember these things. ये याद रखने की जरूरत नहीं है. अभी और एक फार्मूला आने वाला है, वो याद रखना है. We have to remember that. Now V minus e power gamma L and e power minus gamma D divided by V plus e power minus gamma L, then e power plus gamma D. So ultimately this becomes gamma D is equal to, so V minus e power gamma L, that is reflected voltage at load, V plus e power minus gamma L, incident voltage at load. That ratio is actually reflection coefficient at load. Then this is e power minus of 2 gamma D. So this is nothing but gamma D is equal to, what is gamma L from this equation? From this equation, gamma L is nothing but mod gamma L e power j theta gamma L, then e power minus 2. Gamma is actually alpha plus j beta. This is small gamma, that is reflection coefficient. Capital small gamma is propagation constant. Capital gamma is reflection coefficient. Now this one. So separate the magnitudes one side. Gamma D is equal to mod gamma L is also magnitude. E power minus 2 alpha D is also magnitude. Now e power j theta gamma L minus of j 2 beta d is there, j is common, so you get 2 beta d. Okay, so this is at most important formula, students, and this is equation number 4. So this is the formula of reflection coefficient at d distance from load end. So equation 4 is used to calculate reflection coefficient at any location on the transmission line. For example, if you want reflection coefficient at load, then substitute d0. If you substitute d0 here 0, here 0, then you get mod gamma L e power j theta gamma L. That is nothing but gamma L only. Okay, so in that way, any distance you substitute. For example, what is the input in reflection coefficient? For that you have to substitute small d is equal to L, total length of the transmission line you have to substitute. This is very, very, very important formula, student, right? This is at most important formula. So here beta into d. So actually this is a phase. You want this phase, no? So in beta into d is equal to where beta into d is equal to beta is 2 pi by lambda into d. So this is, let us say, equation 5. To get beta d value in radian, transmission line length, that is d here, d is represented. It is represented in terms of wavelengths. So that is important, student. Even though transmission line length is not given in terms of wavelength, like lambda by 2 length transmission line, lambda by 8 length transmission line, they give length of the transmission line and they give frequency, and from that you can find length in terms of wavelength. I will explain that while solving the questions. So if you know the distance in terms of wavelengths, for example, lambda by 2 transmission line, put d is equal to lambda by 2, then lambda cancel, then you get a beta d in radians, then substitute that here, then you will get the angle of reflection coefficient. So this is at most important point. So in any question, if length is not given in terms of wavelength, you have to represent that in terms of wavelength. There are some questions we will solve so that you will understand. Now we found reflection coefficient on the transmission line at d distance. At the meaning of this is actually there is one transmission line like this. So this is ZG and this is VG, let us say, and this one is load, okay, ZL, and this is d is equal to 0. Now you come to d distance from the load end, then reflection coefficient gamma d at this location is this one actually. So anybody ask you what is the reflection coefficient on the transmission line at 3 meters from the load end, then you have to substitute d is equal to 3 meters. That 3 meters is calculated in terms of wavelengths. We will do that later on. So this formula is at most important. You have to remember this one, where I will write these parameters. What is the meaning of Z? What is the meaning of D? I will write here. You see, students. So where small z is the distance measured from, where small z is a distance measured from source end. Z0 means at source or otherwise sending end. Z is equal to total length of the transmission line means at load. This is one thing. So D is the distance measured from load end. Okay. Now D is equal to 0 means at the load end. D is equal to L means at the source end. These are the meanings. So now let us discuss standing wave ratio. Standing wave ratio, SWR. Now already you have seen total voltage at Z distance on the transmission line is in steady state, na? It was Vs is equal to V plus e power minus gamma z plus V minus e power gamma z. So where gamma is equal to alpha plus j beta. Now Vs is equal to V plus e power gamma is equal to alpha plus j beta minus alpha z minus j beta z plus V minus e power alpha z e power j beta z. So voltage in time domain is V of z comma t is equal to real part of steady state voltage multiplied with e power j omega t. So real part of Vs is V plus e power minus alpha z e power minus j beta z j omega t V minus e power alpha z e power j beta z e power j omega t. Now V plus e power minus alpha z, this is e power j omega t minus beta z. Real part is cos of omega t minus beta z plus V minus e power alpha z. So real part e power j omega t plus beta z. So real part is cos omega t plus beta z. So this is V of z comma t. Have you seen? This is similar to the uniform plane wave. There we spoke of electric field. Here we speak of voltages actually. Now for lossless transmission line, alpha is 0, and for lossless transmission line, alpha 0. So V of z comma t total voltage is V plus cos of omega t minus beta z V minus cos of omega t plus beta z. I told you once again, you make this 0, omega t minus beta z 0, then z is equal to omega t by beta. So z positive you got, that means this is wave traveling in plus z direction. Similarly here we get z minus omega t by beta. So this is the voltage wave equation for wave traveling in minus z direction. Okay. So I told you that this is omega t minus beta z, omega t plus beta z. At different locations and at different times, this phases keep changing because here minus is there, here plus is there. At some locations, this phase and this phase become equal, so that the phase difference is 0, e power j0 is 1. In that case, incident voltage and reflected voltage adds and gives maximum voltage on the transmission line. So V maximum is equal to V plus plus V minus. Same as previous chapter, discussing here is wastage of time. Anyway, we are discussing. Now at some locations, for example, the phase of this is 0, this will have 180, the phase difference is plus or minus 180, e power j plus or minus 180 is equal to minus 1. In that case, incident and reflected voltages are subtracted so that you get minimum voltage on the transmission line. Now SWR is defined as maximum voltage by ratio of maximum voltage and minimum voltage. So that calculation you get 1 plus mod gamma by 1 minus mod gamma. Here at some locations on transmission line, incident and reflected are in phase, so they add and give maximum voltage V maximum. So that means that V maximum is equal to V plus V minus, because mod is taken, maybe inside this if minus sign is there, you have to remove that and you have to add. So this is equation number 2. So this is actually, student, this is the voltage, total voltage equation on the transmission line at z distance in terms of distance and time. Okay. Now at some other locations on transmission line, incident and reflected are in opposite phase, that is plus or minus pi. So they subtract and give minimum voltage. Okay, V minimum. So that V minimum is equal to V plus minus V minus. Now standing wave ratio, voltage standing wave ratio, voltage standing wave ratio VSWR is defined as the ratio of V max and V minimum. So that means VSWR is equal to V maximum divided by V minimum, V plus V minus divided by, from this V plus common divided by, here also V plus common. So this cancel, and this is nothing but 1 plus magnitude of reflected voltage by magnitude of incident voltage is magnitude of reflection coefficient. You will not get angle. Similarly, this cancel. This is 1 minus mod gamma, same as previous chapter. Similarly, current standing wave ratio I maximum by I minimum, you get same thing. So VSWR is equal to ISWR is equal to 1 plus mod gamma 1 minus mod gamma you get. So here VSWR is equal to V max by V minimum, and current standing wave ratio is equal to I max by I minimum. Now from this simply we write VSWR is equal to ISWR is equal to SWR. So SWR is equal to 1 plus mod gamma 1 minus mod gamma. We write this as SWR only. From this modulus of SWR is modulus gamma is SWR minus 1 divided by SWR plus 1. Okay. Now we will take different cases, case 1, case 2, case 3. Case 1. Load is open circuit. That means it is open circuit means ZL is infinity. So characteristic impedance. Dear students, in transmission line, this is top conductor, bottom conductor. In between the conductors, you have medium. That medium has G comma C parameters. Because of those parameters, also characteristic impedance came. That is why characteristic impedance is shown between the conductors, indicating that that characteristic impedance has medium parameters also. So load is open circuit, then ZL is infinity, so that gamma L is equal to ZL minus Z0, ZL plus Z0. So infinity by infinity not defined. So that is why you pull the ZL common, then 1 minus Z0 by ZL divided by 1 plus Z0 by ZL. And ZL cancel, 1 minus Z0 by infinity divided by 1 plus Z0 by infinity. This is 0, 1 minus 0 by 1 plus 0 is equal to 1. So in this case, gamma L is equal to 1 you got. Okay, let us say this is equation number 1. Similarly, load is a short circuit. This is simply SC, it is called open circuit na OC. Now in this case, this is characteristic impedance. Now load is short circuited, ZL 0. Now from this reflection coefficient at load is equal to ZL minus Z0, ZL plus Z0. So this is 0 minus Z0, 0 plus Z0, that is equal to minus 1. So this is equation 2. From equation 1 and 2, for both cases, for short circuit as well as open circuit cases, for both cases, mod gamma L is equal to 1. That implies here also mod gamma L is 1, here also mod gamma L is 1. So SWR is equal to 1 plus mod gamma L, 1 minus mod gamma L is equal to 1 plus 1, 1 minus 1 is equal to infinity. So that means in both the cases, standing wave is present. The meaning is that ZL infinity means there is no antenna to receive the energy. Everything is reflected. Here short circuit means there is no antenna device. Whatever signal comes, that is reflected back. So there is a standing wave on the transmission line. Standing wave means not a traveling wave. So in this case, there is no wave propagation on the transmission line, because here antenna, receiving antenna is not there to receive the energy. So this is infinity. Now second case, if ZL is equal to Z0 means there exist receiving antenna, and the input impedance of the receiving antenna is exactly equal to the characteristic impedance. So nothing is reflected. Everything is received by the antenna and radiated into the air medium. That is the meaning. So that is if ZL is equal to Z0, that is called impedance matching at load. So then in this case, this is characteristic impedance and ZL is equal to Z0. Now gamma L is equal to ZL minus Z0, ZL plus Z0, that is the formula. So Z0 plus Z0, that is 0. Now this is mod gamma L is equal to 0. In this case, SWR is 1 plus mod gamma L, 1 minus mod gamma L, 1 plus 0, 1 minus 0, 1. So dear students, here in this case, why we are not writing so much? Because this is same as the previous chapter. So in this case, there is no reflected wave on transmission line, or otherwise there is a pure traveling wave on transmission line. Now I am writing the third point in the note. What is the range of mod gamma? Already we have discussed in the previous chapter. That is, range of mod gamma is 0 to 1, and whenever mod gamma 0, SWR is 1, and whenever mod gamma is equal to 1, SWR is infinity. So this is the range of mod gamma, range of SWR. Next, fourth point, important point. If ZL comma Z0 are real and ZL is greater than Z0, then SWR is equal to ZL by Z0. This is also important formula. I will derive here. If ZL and Z0 are real and bigger one is ZL, so SWR is equal to bigger by smaller. So here SWR is equal to 1 plus mod gamma L, 1 minus mod gamma L, that is equal to 1 plus mod ZL minus Z0, ZL plus Z0, 1 minus ZL minus Z0, ZL plus Z0. So you remove the mod. After removing the mod, it should not be a complex number. Here it is given they are real. So that is why their ratio and their sum and their subtractive value, they never can be complex. They are always real. So that is why if they are real, for example, in exam they give like this. Okay, they give like this. So this is 100 ohm ZL and this is 50 ohm. In between the conductors 50 ohm is written, means that is Z0. So this is ZL. ZL is also real, this is also real, and this is bigger. Now the standing wave ratio is 100 by 50. That is the answer. So that's what we are discussing. If both are real, then it is not a complex number. So if you remove the mod, that should not be a complex number and that should be positive. So ZL is greater than Z0. That means ZL minus Z0 is positive. So that means you remove the mod. So ZL minus Z0, ZL plus Z0, 1 minus of ZL minus Z0, ZL plus Z0. So denominator ZL plus Z0 common, then you get here you get ZL plus Z0, ZL minus Z0, ZL plus Z0 minus ZL plus Z0. So ultimately here 2 ZL divided by the ZL minus ZL gone to Z0, that is equal to ZL minus Z0. This is the calculation, no need to bother about this, you got this one. Similarly, fifth point, if ZL comma Z0 are real and Z0 is greater than ZL. Now bigger one is Z0, so SWR is equal to bigger one by smaller one. Same again, SWR is equal to 1 plus mod gamma L divided by 1 minus mod gamma L, 1 plus ZL plus Z0, 1 minus ZL plus Z0, and both are real, so the ratio is also real. Z0 is bigger, so what to do? After removing this modulus, you have to get positive. For that I will write Z0 minus ZL divided by Z0 plus ZL. Because mod is removed, make sure it should be a positive. So this is reversed. Z0 minus ZL is written, and 1 minus of Z0 minus ZL divided by Z0 plus ZL. So that is equal to now here Z0 plus ZL. So Z0 plus ZL plus Z0 minus ZL divided by Z0 plus ZL minus Z0 plus ZL. So here Z0 gone, and yes, so 2 times Z0 here divided by here ZL, this ZL, no, Z0 gone, so 2 times ZL. So that is nothing but Z0 divided by ZL. So whichever is bigger one, that comes in the numerator. Okay. Anyway, already you know that this I will remove, students. Anyway, you know that SWR in decibels you want, na? Then 20 log SWR you have to take. And also mod gamma in decibels is required. Then 20 log 10 mod gamma is to be taken. Anyway, this much is more than enough. So students, let us observe the standing wave patterns for lossless line. They are not that much important. Anyway, they are like network theory only. Whatever the way you follow in network theory, similar way you can observe these things from network theory knowledge. Let us see now. If ZL is equal to Z0, that means actually that is the impedance matching at load. Then gamma L is 0 actually. So this gamma L is 0. Then SWR becomes 1 plus 0 by 1 minus 0, that is equal to 1. Now, SWR is equal to 1. What does it mean? V maximum by V minimum is equal to 1. That means V maximum is equal to V minimum. And similarly, SWR is equal to 1 means I maximum divided by I minimum is equal to 1. That implies I maximum is equal to I minimum. So that means in this case, on this transmission line, anywhere voltage maximum, voltage minimum equal, current maximum and current minimum equal. So now coming to this discussion, here voltage maximum is equal to voltage minimum. Now let us draw here. This is Z is equal to 0 means at load. I have taken modulus of V. So modulus of V voltage equation on the transmission line, if Z increases, Z is equal to 0 here, no? We were taking D0, that D is replaced again as a Z here. Don't worry, Z is equal to 0 at load. You go like this, then you are going towards the source actually. Now here, so V maximum, it will have some value, let us say 5 volt. This is 5 volt I am representing. That is nothing but V minimum, this one. So it is both are equal. There is no change in that. It is a line. It is also called as a flat FLAT, flat transmission line in this case. FLAT, flat transmission line. So SWR1 is also called as a flat transmission line. Now this is voltage, total voltage versus distance. Now how total current magnitude looks like? Here we know that V by I is Z0. If we will see after some time, if ZL is equal to Z0, then impedance on the transmission line at any location is Z0 only. So V by I is impedance, that is equal to Z0. Now V is equal to Z0 into I. So here definitely I should be less value, because Z0 is always 50, 70 like that. So this is less value multiplied with 50, 60 like that. Then you get V. That means V is always bigger. or otherwise you can see here I is equal to V by Z naught. Z naught is 50, for example, 50 ohm transmission line. So that is why I is smaller. So I is done below this one. So ultimately here, what is the conclusion for examination? For examination, the conclusion is if ZL is equal to Z naught, then SWR is equal to 1. It is called a flat transmission line. In this case, V maximum is equal to V minimum, I maximum is equal to I minimum. So flat transmission line it is called as, and standing wave is not there on this. Pure traveling wave is there in this case. And anyway, here current value is lesser than voltage value. From this, I explained you Z0 is for transmission lines 50, 75, like that characteristic impedance. You will find Z0 value greater than 1. Now it is one line statement here, nothing is there, only single line statement. If ZL is infinity, that means open circuit, then a gamma L is 1, then gamma L is nothing but gamma V. Gamma V means the reflection coefficient of voltage, that is reflected voltage by incident voltage, that is 1. In this case, reflected voltage equal to incident voltage. Then our total voltage waveform, it becomes cos omega t cos beta z. So at a particular time you observe, for example, t is equal to t by 4, this becomes 1. Already we have discussed in last chapter. Then cos beta z, cos waveform, when z is equal to 0, it will have maximum value. You can see when z is equal to 0, voltage will have maximum value, and in this way waveform comes. So after some time I will tell you, actually this is voltage maximum occurs at load, and again after lambda by 2 distance again V maximum comes. So here on the transmission line, voltage maximas or otherwise values repeat for lambda by 2 distance. Values means voltages, currents, impedances, etc. That we have not studied, we are going to study that. So anyway, here there is no use of doing this discussion. Without this, directly I will tell you this one. You know that in network theory, if load is open circuit, then current is 0 there because it is open circuit, and definitely voltage is maximum. That is what this discussion. Current is 0, minimum current is there at load, and voltage is maximum. This much is required. And voltage repeats for lambda by 2 distance, and current minimum here, again that also repeats for lambda by 2 distance. That point we will discuss later on. What you have to observe here in examination, by chance if they give this diagram, in general you won't get these type of questions. Anyway, if you get this, what is the point? Whenever there is open circuit, actually at the open circuit, current is 0. Current is 0 means minimum, and voltage is maximum. So highest voltage at load. That is the main point. After that, voltages and currents repeat for lambda by 2 values. How do you know that? We have not discussed that. We are going to discuss that. Similarly, here now short circuit, students. Short circuit. Whenever short circuit is there, here if you want, I will explain one point actually. If reflection coefficient of voltage is 1, positive, that means V maximum occurs at load, then current reflection coefficient is opposite of voltage reflection coefficient, then that is -1. Here I wrote current reflection coefficient is equal to opposite of voltage reflection coefficient. So whenever gamma L, this gamma L is nothing but voltage reflection coefficient. Whenever gamma L or otherwise gamma V, voltage reflection coefficient, is positive, positive means they add incident voltage and reflected voltage, you get maximum. Whenever gamma I is negative, they subtract reflect the current and incident current, then you get the minimum voltage. No need to analyze. If positive is there, maximum voltage maximum. If current reflection coefficient negative, you get voltage current minimum. Current minimum in that way. So here you can see, without analysis directly we will discuss. ZL0 short circuit. Whenever there is a short circuit, then voltage drop across that circuit. Short circuit is 0. Voltage drop 0 means minimum voltage. You can see here voltage is minimum. This is voltage waveform. This one is voltage waveform. And on this axis we are taking voltage as well as current, we are taking both. Here also voltage as well as current magnitude we are taking both. So voltage 0, and whenever there is a short circuit, through that short circuit maximum current goes, so that is I maximum. If you want equation wise, once again I am telling, where if there is a short circuit, current is maximum through that short circuit. So at the load itself short circuit is there, so at load, that means Z is equal to 0, maximum current is there, and through the across the short circuit voltage 0, so at load short circuit is there, so that is why voltage at the load is 0. Then on values repeat for lambda by 2 distance. For example, I maximum is here, again that value repeated for lambda by 2 distance. We will study that later on. So here if you want equation wise, if you want ZL 0, then gamma L is minus 1. Gamma L is nothing but gamma V. So if gamma V is negative, then whichever reflection coefficient is negative, then that value becomes minimum. Voltage reflection coefficient negative, then voltage minimum at load. So current reflection coefficient is opposite of voltage reflection coefficient. So current reflection coefficient is positive, then whichever is positive, that value is maximum. So current reflection coefficient is positive, that means maximum current is found at load actually. So similarly here, you should understand one thing here, dear students. What is that? Here and in this case and in this case, SWR should be infinity, student. 1 plus mod gamma, 1 minus mod gamma, infinity. So SWR infinity means you should understand that V maximum divided by V minimum. So definitely V minimum should be 0, so that then only you get what do you say, SWR infinity. That is why this voltage here axis is 0. Here if current touches this one, that is 0 current. If voltage touches this one, that is 0 voltage. Similarly here also, because reflection coefficient is 1, SWR is infinity. In that case the minimum voltage or otherwise minimum current is 0 here. They touch this one. If SWR is not infinity, greater than 1, that means these values, minimum values does not touch 0, they will be little upper. Anyway, here if ZL and Z0 are real and Z0 is greater than ZL, in this case SWR already we have seen, bigger one here, yeah, Z0 is greater than ZL, then in this case SWR is equal to bigger one by smaller one, that is always greater than 1. So here it is not infinity, we want to say. If not infinity, then these minimum values are not equal to 0. Okay, anyway, that is not that much important. You see this one, gamma L is ZL minus Z0, ZL plus Z0. Z0 is bigger, then gamma L is negative. If gamma L is negative, then this gamma L is nothing but this voltage reflection coefficient. Gamma L is voltage reflection coefficient. So here gamma L is equal to voltage reflection coefficient, that is negative. That means you should understand at load V minimum is there. I told you if voltage reflection coefficient is negative, then incident and reflected voltage subtract, you get minimum voltage. Yes or no? So and this current reflection coefficient is opposite of voltage reflection coefficient, so that is positive. Current reflection coefficient positive means reflected current and incident current have same sign, they add and gives maximum current. That means maximum current at load is there in this case. You can see here maximum current at load. Don't confuse, the V maximum is not at load, V maximum is here at this distance, V maximum. So here you can see only I maximum is there touching this Z is equal to 0, and voltage minimum also should touch. This one is the voltage minimum. Okay, and similarly here what you have to understand is if this line and this line are not touching this line, that means their values are not 0. In that case SWR, that means I minimum, V minimum are not 0. Then in SWR denominator you will not get 0. That means SWR you will never get infinity in this case. That means here partial standing wave and partial transmitting wave is there in this case. Now here case 5, if ZL and Z0 are real and ZL greater than Z0, this is the opposite case of this one. Then in this case, SWR is ZL divided by Z0. SWR is equal to ZL by Z0, that is greater than 1. So if you calculate the gamma L, ZL minus Z0, ZL plus Z0, here ZL is bigger, so that is why gamma L is positive. Gamma L is nothing but gamma V, that is positive. At the load, V maximum is there. Gamma I is opposite of gamma V, that is negative. At load, I minimum is there. That means these diagrams are exactly opposite of that one. Okay, right. So, dear students, now impedance of the transmission line. Actually, anyway, I will be doing derivation. I told you you should not study the derivations, and whatever formula we get, that is very important. Applications of that formula we have to see. So anyway, I am doing the derivation. You keep watching. So what is going on, you can understand. So can you recall the diagram of the transmission line? Here, you know that this is the first conductor and this is the second conductor, dear students. Okay. Now, this is the generator internal impedance. This is the plus minus generator voltage here, and here this is Z is equal to 0. At Z distance, we know the equations of the voltage and current already we know. So V of Z and I of Z, we know the equations. Now, at load, so in some books they call it as a ZL. ZL means load impedance. In some books they call it as a Z suffix R. Here ZR means receiving end impedance, that is nothing but load impedance. So this is also called as receiving end or otherwise load end. Okay. So exactly I will maintain the same distance. Okay. Now this D is equal to 0 means at load. Now you came to D distance. You came to D distance from the load actually. Okay. So anyway, dear students, can you tell me what is the voltage equation at Z distance on the transmission line? Already we have written. So that is nothing but V minus e power gamma Z plus V plus e power minus gamma Z. This is equation number 1. Similarly, can you tell me what is current equation at Z distance? I minus e power gamma Z plus I plus e power minus gamma Z. So let us write I minus I plus in terms of V minus V plus. This is nothing but minus of V minus by Z naught. This already you know, students. So e power gamma Z plus I plus is V plus by Z naught e power minus gamma Z. So this is I of Z equation in terms of voltage. Okay, this one. Here minus sign is there. Now actually what is the voltage at load? So voltage at load, this one. What is the current at load? IL. First of all, I am writing one equation here. ZL is equal to impedance at load is equal to voltage at load divided by current at load, that is nothing but VL is equal to ZL into IL. So I will call this as equation number 3, right? Okay. Now from equation 1, if we put Z is equal to total length, so in some books they take this total length as a small l, in some books they take it as a capital L, doesn't matter, it is total length. So dear students, in equation 1, Z0 means at source end, you substitute small z is equal to L, substitute small z is equal to L, then you get the voltage, total voltage at load you get. So if we put z is equal to L in equation 1, then what you get, this VL, that is nothing but VL means total voltage on the transmission line at the load. So that is nothing but VL, student, is equal to V minus e power gamma L plus V plus e power minus gamma L. Okay. Now what you do, this equation 4, actually this is a voltage at load in terms of V minus e power gamma L, V plus e power minus gamma L. Same VL is obtained if you know ZL and IL. That means this VL and this VL same. So put equation 3 in equation 4, then what you get is IL ZL is equal to V minus e power gamma L, V plus e power minus gamma L, equation number 5. Similarly, dear students, if we put Z is equal to L in equation 2, so that means this equation, if you put Z is equal to L, that means Z0 means at the source, you put Z is equal to L means you come to the load, then you get IL, current at the load you get. So here L you substitute, then you get IL, that means total current at load you get. So then what you get is IL is equal to minus V minus e power gamma L divided by Z0 plus V plus divided by Z0 e power minus gamma L. Now IL Z0 is equal to minus of V minus e gamma L plus V plus, because Z0 I send this side, so e power minus gamma L. This is equation number 5. Equation number 6. We are going to find V minus comma I plus in terms of ZL and Z0 we want to find. For that, what you do, you add equation number 5 and equation number 6. That implies, can you see here, if we are adding means you are adding this and you are adding this. That means IL ZL plus IL Z0 is equal to V minus e power gamma L, V minus e power gamma L. Same, here plus is there, here minus is there, they cancel. And V plus e power minus gamma L, V plus e power minus gamma L, 2 times V plus e power minus gamma L. So from this, actually from this one you can find V plus. So V plus is equal to IL common, then ZL plus Z0, okay, divided by 2 and e power gamma L. Let us say this is equation number 7. So if you subtract them, equation 5 minus 6, shall I do? Yeah, equation 5 minus 6. Equation 5 minus 6 implies, this means minus comes here, plus comes here, minus comes here. Then IL ZL minus IL Z0. So this add, and here plus comes, here minus comes, students. So that this one adds, this cancels. So ultimately you get 2 times V minus e power gamma L. So here V minus is equal to IL common ZL minus Z0 divided by 2. Next e power minus gamma L. Equation number 8. What we have done here, students, in this equation there V plus V minus is there, in this equation also V plus V minus is there. Then we have calculated V plus V minus values in terms of IL, ZL, Z0, and of course e power gamma L, e power minus gamma L, we have calculated them. Now let us substitute equation 7, 8 put equation 7, 8 in equation 1, 2. Now we get V of Z is equal to V minus, in place of V minus, we are going to put this one, IL ZL minus Z0 divided by 2 e power, there gamma is there. So first V minus we are substituting, na, here V minus we are substituting, e power gamma Z, here e power minus gamma L, gamma is common, so e power gamma common, Z minus L you get, right, plus substitute this V plus here, then you get IL ZL plus Z0 divided by 2 e power, here e power gamma L is there, here e power gamma Z is there, e power gamma common, so e power gamma common, L minus Z you get. So this is equation number, what do you say, 9. Similarly, you substitute V minus here. If you substitute V minus there, then what will you get? IL minus sign is there, that comes here. So Z0 minus ZL, then divided by 2, already Z0 is there, then e power minus gamma L is there here e power gamma Z is there, so e power gamma common, so then Z minus L you get, plus substitute V plus here, then you get IL ZL plus Z0 divided by 2, already bottom side Z0 is there, so e power plus gamma L is there, so gamma common, then here e power minus gamma Z is there, so L minus Z comes here. Okay, so this is equation number 10, dear students. Now you know that here I am writing here, if Z plus D is equal to L, then Z from sending end, D from load end give same location, then Z comma D give same locations. Okay, so here D is equal to L minus Z, D is equal to L minus Z. Okay, so now what I do, what is the impedance of the transmission line at any distance? Impedance of the transmission line at any distance means, for example, at Z distance, total voltage V of Z, total current I of Z, total voltage of transmission, total impedance of transmission line at Z distance is equal to, total impedance of transmission line at Z distance is equal to voltage at Z distance divided by current at Z distance. That means this is the equation, voltage at Z distance by current at Z distance. So capital Z means impedance at Z distance is equal to voltage at Z distance by current at Z distance, that gives here V of Z is this one, dear students. So numerator, anyway some terms are going to cancel here, okay, let them be like this. Okay, IL by 2 cancel, no? You can see here, students, if you take this ratio, no students, anyway IL by 2 cancel, and the denominator current, no, denominator Z0 is there, it comes to numerator, so ultimately you get Z0, okay, then Z0, then ZL minus Z naught e power gamma, just a moment student, I am doing some adjustment there. So D is equal to L minus Z. I will write this as a L minus Z. Okay. Okay. Here Z minus L is there. So I will write L minus Z, minus of K, plus then here ZL plus Z naught e power, already L minus Z is there. I am writing L minus Z. I will tell you why. Next, here this one Z naught minus ZL, here I want to write L minus Z. So e power minus gamma L minus Z plus this one ZL plus Z naught and e power gamma L minus Z, students. So let us say this is equation number 11. Already we know that Z plus D is equal to L. That implies L minus Z is equal to D. So L minus Z is equal to D. Okay. If we put L minus Z is equal to D in equation 11, then we get impedance of transmission line at D distance from load. I have done same thing student in previous case also. Did you remember? While finding the reflection coefficient equation, I have substituted this relation. If I substitute this relation, then only it is guaranteed that small z distance from load end and small d distance from mistake. If I substitute this relation, then only small z distance from the source end and small d distance from the load end give same location. That is why that substitution is done. If you don't substitute that relation, then it is not guaranteed small z distance from source end and small d distance from load end give same location. So it is not guaranteed. So that is why if you substitute L minus Z is equal to D in equation 11, then we get impedance of transmission line at D distance from load, that is called as a Z of D. So now capital Z means impedance, D means capital Z means impedance. Impedance of transmission line at small d distance from load, that is the meaning, is equal to Z naught here ZL minus Z naught L minus Z is equal to D, student, e power minus gamma D plus ZL plus Z naught e power gamma D divided by Z naught minus ZL e power minus of gamma D plus ZL plus Z naught e power, this is L minus Z is equal to D, so this is gamma D. Now this gives Z naught, here ZL you common, ZL no, so e power gamma D plus e power minus gamma D. Next Z naught you common, student, Z naught plus Z naught, then e power gamma D minus e power minus gamma D, okay, divided by, here Z naught you common, then e power gamma D plus Z naught into e power minus gamma D, next plus ZL you common, ZL, so ZL you common, then e power gamma D, then minus of e power minus gamma D. So you students know that e power gamma D plus e power minus gamma D gives cos h gamma D. Of course by 2 should be there. Here also you put by 2, here also you put by 2, here also divided by 2, divided by 2. So numerator denominator divided by 2, so nothing happens. So that is why this becomes now z of d is equal to dear students, that is z naught zl, this one is cos h gamma d, cos h gamma d, and plus any students confusion, then you do one thing, put divided by 2, put divided by 2, so divided by 2, divided by 2. Now here divided by 2, here also divided by 2, nothing will happen to that equation. Okay, cos h gamma d, then plus z naught, this one is sin h gamma d divided by this one z naught, plus is there no, cos h gamma d plus zl sin h gamma d. So this is the equation you got. Now you common cos h gamma d, cos h gamma d, then divide with cos h gamma d, it becomes tan h gamma d. So this is the equation which you have to remember. So z naught zl plus z naught tan h gamma d divided by z naught plus zl tan h gamma d. So this is the equation which you have to remember. I will be writing this in the note, equation number 12. This is for general transmission line, and where z naught is equal to root of r plus j omega l divided by g plus j omega c, and gamma is equal to of course r plus j omega l and g plus j omega c, that is nothing but alpha plus j beta gamma. Now for lossless transmission line, z naught is equal to root L by C, that is called real characteristic impedance, and gamma is equal to j omega root LC, that is called j beta. So in this case tan h gamma d is equal to tan h gamma is j beta, so j beta d, so that is equal to j tan beta d it becomes. Okay, then this equation 12 becomes z of d is equal to, now anyway, even though it is real characteristic impedance, you can write that z naught only, no problem. So z naught, then zl plus jz naught tan beta d divided by z naught plus jzl tan beta d. Okay, so this is the anyway, if you are remembering this formula, simply in place of tan h gamma d, j tan beta d, how to substitute for lossless transmission line. Once again I told here, beta is 2 pi by lambda, so that is why d is always represented in terms of wavelengths. Okay, now we are going to write note by taking the various lengths. We will see that short circuit, open circuit, those things we will discuss. Okay, dear students, now see this one. Basically, if you take the transmission line, this is ZL, and this is length of the transmission line, total length L. D is equal to 0. Now at a D distance, at d distance. What is the impedance of the transmission line? So if Z0 is the characteristic impedance, then Z at a d distance is equal to Z0 into ZL plus Z0 tan H gamma d divided by Z0 plus ZL tan H gamma d. Okay, that formula I kept that in the box. Actually, you have to remember that in previous topic, this formula I kept in the box. Now, if ZL is equal to Z0, dear student, if ZL is equal to Z0, that means there is a matching at the load. There is a matching at the load. Then what happens in this formula? Z of D, whenever ZL is equal to Z0, then what will happen? Z0, so Z0 plus Z0 tan H gamma D divided by Z0 plus Z0 tan H gamma D. So this one cancel. Ultimately, you get Z at any distance of the transmission line when ZL is equal to Z0 is Z0. This one cancel. Conclusion is that if load is matched with the characteristic impedance, then for that transmission line at any location at load as well as at d distance as well as at input also, independent of the distance, the transmission line impedance is equal to Z0. That means everywhere it is matched, so that there is no standing wave, or otherwise there is no reflected wave. If there is no reflected wave, then definitely there is no standing wave. So if ZL is equal to Z0, then at any distance on transmission line at any distance on transmission line impedance, or otherwise transmission line impedance is Z0. So this point you have to remember. So if ZL is equal to Z0, that means load is matched with its characteristic impedance. Then at any distance on the transmission line impedance is Z0. Okay. Now, one observation I am writing, dear students. In the observation, if any note comes, you have to put that in the box actually. Okay. First one, load is short circuit. Okay. That means ZL is equal to 0. If load is short circuit, then let us say total length of the transmission line is L. ZL is equal to 0 or D is equal to 0. Then if I substitute D is equal to L, if I substitute D is equal to L, then what does it mean? I came to the input, then I am finding input impedance. So this is called input impedance. When load is short circuit, Zin of SC it is called as Zin of SC. So Zin of SC means, here meaning is Zin means input impedance. Suffix SC means when load is short circuit. When load is short circuit. Now let us find that impedance. Actually, Z at D is equal to L. That means I am finding impedance of the transmission line at D is equal to L. and I am substituting ZL is equal to 0, then that formula is this one. So you substitute D is equal to L, then gamma L you get. Then ZL 0 means here 0 you get. So Z0 by Z0 cancel. Then Z0 tan H gamma L you get, students. Okay. So you can write here Z0 then 0 plus Z0 tan H gamma L divided by Z0 plus 0, Z0 gone. So we are calling this one D is equal to L means at the input, ZL 0 means short circuit. So input impedance when load is short circuit, that is Zin of SC is equal to Z0 tan H gamma L. So simply this is also called a student, so many suffix are there na, it is called a ZSC. क्योंकि बहुत बड़ा हो गया इधर नाम, इसलिए थोड़ा कंफ्यूज होता है. इसको जेड इन इनपुट इम्पिडेंस व्हेन लोड इज शॉर्ट सर्क्यूट, इसको ZSC भी बोलते रहता है. सो ये ZSC है, ये दिस वन इज इक्वेशन नंबर 1. हैव यू सीन स्टूडेंट, if it is a lossless line, then gamma is equal to J beta. So then this becomes a tan H J beta L, that is nothing but J Z0 tan beta L it becomes. Anyway, that is next, we will discuss that next. So second one, load is open circuit. It is symbolized as OC. Now for this ZL is equal to infinity, dear students. Okay. Now in this case, total length of the transmission line is L. Now here ZL is equal to infinity, open circuit. So Z0 is the characteristic impedance in both the cases. D is equal to 0 means at load. D is equal to L means sending end. So that is Z in OC, that is also called ZOC. So ZOC is nothing but input impedance of transmission line, input impedance of transmission line when load is open circuit. When load is open circuit. Okay. Now when you substitute Z impedance, impedance of the transmission line when D is equal to length, that means you come to the input, then ZL is equal to infinity. Then what you do, students? Here, if you substitute ZL is equal to infinity in this ZL infinity, you substitute infinity by infinity becomes not defined. So L hospital rule. Then you pull ZL here, ZL common. Then automatically here by ZL comes, here divide by ZL comes. Then again ZL is equal to infinity, you substitute. Automatically denominator tan H gamma D remains. It goes to numerator, it becomes cot H gamma D it becomes. So Z0, then ZL is common. So 1 plus Z0 tan H gamma L divided by ZL divided by Z0 divided by ZL plus top one, Z0 by ZL, then tan H gamma L. Is this right? So ZL 1 remains. So now it is fine. You substitute now ZL infinity here. So something by infinity is 0. Here also something by infinity is 0. Now this is 0, this is 0. Now Z0 by tan H gamma L remains. So that is Z0 cot H gamma L. So now D is equal to L means input. ZL is equal to infinity means load is open circuit. So it is symbolized as ZOC. It is symbolized as ZOC. इसको symbol दे दिया हमने, ZOC करके दे दिया. So this is Z naught 1 by tan H gamma L becomes cot H gamma L. So this is equation number 2. So right. So dear students, equation 1 multiplied with equation 2, what you get? Equation 1 multiplied with equation 2 implies ZSC multiplied with ZOC is equal to Z0 into Z0 is Z0 square. Then tan H gamma L, cot H gamma L is 1 by tan H gamma L. They cancel, you get this one. Ultimately, characteristic impedance is equal to root of ZSC and ZOC. This is important formula you get in objective questions. So this is equation 3. In examination, they give ZOC is 100, then ZSC is 50. Then what is the characteristic impedance? Multiply them and take the root actually. So you put them in the box so that you know the meaning of them. This one also. Okay. So whenever you see this observation, read this. रिविजन कैसे करना है, ये ऑब्जर्वेशन देखने के बाद आप लोग ये बॉक्स में जो है वो पढ़ लीजिए. ZSC मतलब इनपुट इम्पिडेंस ऑफ द ट्रांसमिशन लाइन व्हेन लोड इज शॉर्ट सर्क्यूट. Similarly, if you want, you can remember this equation. Then this one ZOC means input impedance of transmission line when load is open circuit. Then this is the equation. This is very important equation. So how to find the characteristic impedance of the transmission line experimentally? Measure input impedance of the transmission line when load is open circuit. Then second case, measure input impedance of transmission line when load is in one case short circuit, in other case open circuit. Then you multiply those impedances and take root, you get Z0. So equation 1 divided by equation 2, that implies ZSC divided by ZOC is equal to Z0, Z0 cancel. Numerator tan H gamma L divide with cot H gamma L. So it becomes tan H square gamma L. Now from this tan H gamma L is equal to root of ZSC divided by ZOC. From this gamma L is equal to gamma L is equal to tan H inverse of root of ZSC by ZOC, that is gamma into L. Now we want gamma, so 1 by L you take, 1 by L you take. So this is the formula for gamma if you know length and ZSC and ZOC. So equation number, this is the 4. It is not that much important, okay type, but this is very important formula. Okay. So after this, we will take the lossless transmission line, then we will do the discussion. So students, now let us discuss short circuit and open circuit at the load for lossless transmission line. We have discussed till now general transmission line. Now for lossless transmission line, first short circuit lossless transmission line. So here one transmission line is there like this, and total length is L, let us say. Then it is short circuit here, so that ZL is 0, short circuit. D0 means at load. Then substitute D is equal to total length. We come to the input. So this is called Zin. Okay, input impedance when load is short circuit. Now for the lossless transmission line, Z of D is equal to Z0 into ZL plus ZZ0 tan beta D divided by Z0 plus JZL, it becomes tan beta D. Here at d distance, that is the equation. Now we have to substitute d is equal to L, and also ZL is 0. So shall I write here? Okay, I will write here. Z impedance, when I substitute d is equal to L, that means that becomes input impedance when load is short circuit. Then from this formula Z0, so ZL is equal to 0, you substitute, then 0 plus JZ0 tan beta d divided by Z0 plus 0. So this is called input impedance when load is short circuit. ZSC it is called as. Now for time being you call it as a Zin. So this is basically Z0 cancel, JZ0 tan beta d. Okay, let it be like this. Now I am writing here a few points. You keep watching. At d is equal to 0. Anyway, d is equal to 0, short circuit is there. Impedance is 0. Definitely you should get 0 impedance. Let us see. D0 implies beta d is equal to 0. That means Zin is equal to J Z0 tan 0 is equal to 0. You got 0. So at d is equal to lambda by 4 distance. Okay. Then beta d is nothing but beta is 2 pi by lambda, d is lambda by 4. That is nothing but lambda cancel, you get pi by 2, na? Lambda pi by 2 you get. That implies Zin is equal to JZ0 tan beta d is pi by 2 here. So ultimately you get J, this is infinity, J infinity you get. Okay, J infinity, but angle is pi by 2. At d is equal to lambda by 2 implies beta d is equal to, beta is 2 pi by lambda, d is lambda by 2, lambda cancel, you get pi, this is the angle. So now Zin is equal to JZ0 tan pi, that is equal to tan pi is 0 actually. Similarly, 3 lambda by 4 like that. Okay, 3 lambda by 4 like that you see. And at d is equal to 3 times lambda by 4, no? Then beta d is equal to 2 pi by lambda. D is nothing but 3 times lambda by 4. So lambda gone. Now you get 3 times pi by 2. This is the angle. Now Zin is equal to JZ0 tan 3 pi by 2 is written as pi plus pi by 2. Okay, 3 pi by 2 is written as pi plus pi by 2. This one is which quadrant? Third quadrant. So yeah, this is the third quadrant. Of course, 270. Yeah, it is about to become again infinity, na? This one. So anyway, it is infinity value, and tan. Okay. Actually, this becomes infinity. Now, if we see this value, if we see this diagram actually here, I will take here. This is a D. On the vertical axis, I will take Zin, that is nothing but JZ0 tan beta d. Now it is JZ0 tan beta t. Top side is a positive reactance. I am taking. I will write here, na, positive reactance, because this side waveform will come. This is actually negative reactance. Okay, let us mention करेंगे इधर. First one is 0 distance, then okay, that will be coming like this. Anyway, here when d0 the impedance is 0, then when lambda by 4 it goes to infinity. So it is like this, dear students. Then whenever j infinity, that is infinity, j infinity it is going, then this is first quadrant. Then angle is little bit increased, no students. Then it goes to value is infinity only, but it goes to second quadrant. So tan is negative in the second quadrant. So that is why it starts here again. And this value is what distance is what, lambda by 4. Next distance comes actually this much, this much. Next distance comes lambda by 2. So now at lambda by 2, what is the value? 0 you got. So here I will put 3 times lambda by 4. This is 2 times lambda by 4 means that is lambda by 2. So like this. Okay. This much is more than enough, dear students. Right? Now objective question starts. Till now nothing happened, objective questions. Now I am going to ask you the questions. These are all standard questions actually. First one. Question is short circuit transmission line. That means load is short circuit. Short circuit transmission line. The length is pi by 4. Behaves like a answer inductor. Because when load is short circuit, then input impedance, here you see positive reactance, because tan beta d value in this range is positive. That means jz0 into positive, jz0 input impedance, positive input impedance, that is inductor actually. Inductor gives a positive input impedance. So first question is that short circuit transmission line for 0 what do you say, less than d. D means total length of the transmission line. Lambda by 4. Short circuit transmission line for this distance behaves as inductor. Behaves as inductor. ये है objective question. It behaves as inductor. That is the answer. So you know why? Because Zin is equal to jz0 tan beta d. For this jz0, this is positive value. Ultimately jz0 into some positive value plus jz0 some value you get. So that is inductance impedance only you get positive. Okay, this one. So the equivalent circuit is like this, inductance. Now the second question, dear students. Short circuit, that means load, transmission line for you can see here lambda by 4 to lambda by 2. Lambda by 4 to lambda by 2 behaves as, you see here, lambda by 4 to lambda by 2 distance. For this distance it behaves as, actually here it is negative value, so it behaves like a capacitor actually. So the input impedance is negative, so the transmission line behaves like a capacitor, behaves as a capacitor. because Zin is Jz naught tan beta d. So ultimately Jz naught into negative. So minus Jz naught. Actually, I am not bothered about magnitude, student. Only sign I am taking here. So this is capacitance. Now, third question is that these are all questions, students. Short circuit transmission line at d is equal to exactly lambda by 4. Total length is lambda by 4. Okay. For total length d is equal to lambda by 4, behaves as. So the answer is actually a combination of these two, inductor and what do you say, parallel combination of inductor and capacitor. So this is the answer, students. Or otherwise you can write like this also, parallel combination. Okay. So inductor and capacitor parallel combination. Because you can see here d is equal to lambda by 4, no? Lambda by 4, just exactly lambda by 4. Plus j infinity minus j infinity, both exist. And value is infinity. That happens for parallel circuit in the network theory. Impedance is plus or minus j infinity for parallel circuit. Similarly, at lambda by 2 distance, exactly you can see plus minus 0. That happens, impedance is plus minus 0 for series circuit actually. So that one is short circuit transmission line for d is equal to lambda by 2 behaves as a series combination of L and C, students. So this is the answer. Actually, no question itself they will ask short circuit transmission line for D is equal to lambda by 4 behaves as option A, inductance, option B, capacitance, option C, parallel combination of inductance and capacitance, option D, series combination of. Then answer is this one. So these are 4 questions actually you have to understand and remember them. Okay. So students, now case 2, this is actually open circuit lossless transmission line behavior. Let us see now. So in this case, you take the transmission line and here ZL is infinity, that is open circuit actually, D0. So L is total length of the transmission line and D is equal to L. So this is input impedance. Okay. Now for lossless line, Z of D is equal to Z naught ZL plus J Z naught tan beta D divided by Z naught plus JZL tan beta D. Okay. Now from this what I do, I will write like this, Z naught 1 plus J Z naught by ZL tan beta D, because we have to substitute ZL is equal to infinity, no? So that is why J tan beta D. Now if you substitute D is equal to L, that means input, and ZL is equal to infinity, then we get Z naught 1 plus J Z naught divided by infinity tan beta D divided by Z naught by infinity plus J tan beta L. So this is nothing but input impedance when load is open circuit and ultimately this is 0, this is 0, 1 by j tan minus j. So minus j z naught cot beta L. So if I draw the diagram of this, so d is equal to 0 here, and no need to put d there. So it is 0 here. Then it is let us say lambda by 4. Then it is lambda by 2. Okay, 3 times lambda by 4, then this is lambda. Like this. Now this value, if I take this on the what do you say, Zin is equal to minus j z naught cot beta L if I draw, and this is positive, थोड़ा बड़ा लिखेंगे, पॉजिटिव रिएक्टेंस. अगर ऊपर कर्व है तो पॉजिटिव रिएक्टेंस है. मैं ये नहीं बोल रहा हूँ ये पॉजिटिव आ गया करके नहीं बोल रहा हूँ, कन्फ्यूज मत हो जाओ. अगर कोई कर्व ऊपर आएंगे तो वो पॉजिटिव रिएक्टेंस है. इफ कर्व कम्स टॉप साइड, दैट इज पॉजिटिव रिएक्टेंस. Then if any curve comes bottom side, that is negative reactance. So now the curve is like this. Here it is going like this. You can calculate the values if you want. So here once again questions are like this. Open circuit transmission line. Of course, lossless student. We are discussing only lossless. Open circuit transmission line for a total length 0 to lambda by 4. Okay, 0 to L, or otherwise D you can take total length 0 to what do you say lambda by 4. That means from here to here 0 to lambda by 4. Here the overall value is negative. That means that is capacitor for behaves as, because Zin is actually what do you say negative, no? Here you can see. That means minus j z naught cot beta L. You can calculate same as previous one. You get negative reactance curve also you can see. So equivalent circuit is a capacitor here. It behaves like a capacitor actually. That is the answer. Behaves as answer capacitor. Behaves as capacitor. Second question. Open circuit transmission line for lambda by 4 to lambda by 2 distance behaves as, of course Zin is this one formula cot beta L. That means it is a positive reactance, that is inductor. That is, it behaves like inductor. That is the answer. Okay, you can see here. This is positive reactance. This one lambda by 2 to lambda by 4 to lambda by 2. Then open circuit transmission line for exact length lambda by 4 behaves as you can see here, na 0 is there, plus minus 0. Just below this it behaves like minus 0. Just above the lambda by 4 it behaves like plus 0 impedance. That is series circuit actually. Behaves as series combination of L and C. That implies this one. Okay. Now open circuit transmission line for L is equal to lambda by 2 behaves as a parallel combination of LC so this is the answer. Okay.